Hi, let me begin with week 8 discussion. In this week, we'll see what has been done. We'll solve some exercise questions. Okay, so let me start with notation which is given in exercise note. G can be nth root of unity, primitive nth root of unity. Primitive means this is written in generator of the cyclic group. This is cyclic group. And D10 is generator of this group. Okay, so nth cyclotomic field extension is denoted as this, which is just we are attaching nth root, primitive nth root of unity to Q. And this D10 belongs to C, and it is nth root of unity in C. And we also noted that this extension, degree of extension is equal to phi n, where phi n is Euler phi function of n, which is equal to degree of phi x. Phi x is minimal polynomial for zeta n. Okay, so Q1 is a splitting field of phi nx. Oh, this was phi nx over Q, where and hence zeros of this phi nx, minimal polynomial of zeta n, are precisely the generators of mu in C, because phi nx degree is phi n, and generators of mu in C, which is mu in C is nothing but then star, and generators of this are generators of Zn star. Order of this is also phi n. So they are exactly the roots of these polynomials, phi nx, phi nx. Okay, so these are all equal. Degree of nx is same as phi n, and same as this degree of extension. Finally, recall that Galois extension, Galois group is isomorphic to Zn star. Yeah, so this is all done inside in the class lectures. So let me start with some exercises. So question number 8.1, which is given P be prime number and let L be splitting field of x power p minus 2, then so that L is Q attached with A and zeta p. Zeta p is pth root of unity inside complex number C. Okay, let me see 8.1. A part A. What is given is that L is the splitting field of x power p minus 2. So in particular, where p is prime, p is prime number. So how to do this? L is the splitting field of this polynomial. So for example, this first let's check f is equal to x power p minus 2. is irreducible. Irreducible over Q. How? Because of Einstein criteria. For irreducibility. So because for example 2 does not divide. Okay, whatever. This is irreducible. Let you check it. Okay, so it is irreducible in particular because Q is of characteristic 0. So this is separable polynomial. F is separable also. Fx is separable polynomial. Since whatever roots of F are, they are distinct. And what are root of F? Is square root, not a square root of 2. Pth root of 2, which belongs to real number, is one of the root of F inside real number. Okay, F is polynomial over Q. What else roots are? V, C, F. This can be written as you just have. I'm just giving you an idea. This, let's say this is your A, and A into zeta P, A into zeta. Let me write xi, okay, because I'm not good to write zeta. So let A xi P square and so on. For me, zeta is same as zeta, okay? So don't go to notational problem, okay? So here A zeta P power P minus 1. So this pattern stops here because next time when I will write A zeta P power P, zeta power P will become 1. So it will become A only. So this stops. So this is a set that without repetition, no repetition happening in set. So this is a set. Cardinality of VCF is equal to P. Okay, so why P? Because no repetition is happening. Why this is satisfying the polynomial F? Take anything, A into zeta P power I, and apply on F. What will get? A zeta P power I whole power P minus 2. This is our F. And what will happen next? It will become A to the power P into zeta P to the power IP, which you can write zeta P I outside minus 2. But A power P is just 2, right? From here. So it is 2 into zeta P power P is 1. 1 power I is 1. And this becomes 0. So all of these are roots of F. Okay. So no worries for that. How, why cardinality is equal to P? That is because if you take any of two of them are equal, let's say zeta P power I is equal to A into zeta P to the power J. I and J both are less than P, then because A is non-zero and R is a real number. Complex number is a field, so A will cancel out because A is non-zero. So this can be written as zeta power I minus j is equal to 1. And I and j both are, this is true or this is true. J minus I, whatever is bigger. For example, let me write explicitly. I and j I am taking distinct for time being, otherwise they are anyway equal. So for I and j not equal, so we can take I less and j bigger. Such a case is happening, then what will happen is that from this relation, we can take I j minus I is equal to 1, and this is contradiction because zeta p is primitive root. So all of these are distinct. Zeta p, zeta power square, zeta power p minus 1, these are distinct. So only first power p is there when zeta power p becomes 1, otherwise not. This is contradiction. So this is we have VCF of cardinality C. All of them are distinct. We have p roots, separable p roots. So L is a splitting field. So what is L? Hence L is equal to, we will attach all of these roots. What are these roots? A zeta p, A zeta p square, and so on. A zeta p, p minus 1. Okay, so we have to show, this is our question mark, if this is same as q a zeta p. Okay, how will we say? One direction is obvious, na? This is our claim. So let us see the proof of this. A belongs to L. This is clear. Q is subset of L. This is also clear. But zeta p, this can be written as A zeta p or by A. This belongs to L. This also belongs to L. So the quotient, because L is field, this belongs to L. So all this together implies Q A zeta p. This is a subset of L, right? What about other direction? Other direction is obvious, right? A belongs to Q A zeta p. In particular, A zeta p or I, because zeta belongs to Q A zeta p. So any its power and multiplying by A, this all belongs to Q A zeta p or any I. So this implies L and Q is anyway subset of QAP, Q zeta p. So this implies L is subset of Q A zeta p. So this is done. Okay, so I hope you understood this. If you have doubt, you can write into comment box. Okay. Describe generators of Galois group with their action on A and zeta p. So is this Galois extension? Okay, this is Galois or not, it will be clear in a moment. For that, we have to see that Galois group is isomorphic to, Galois group is order of the Galois group is equal to the degree of extension, right? Then only we can see that Galois group is, this is Galois extension. So the question is of extension. L over Q is a Galois extension. How to see that? So for that, first we have to calculate what is degree of extension. Okay, so we have seen that L is equal to Q A zeta P. Okay, but this extension can be written as Q A and then here over Q. So minimal polynomial which satisfies A, this is Galois extension or not? It is not clear. But A satisfies the polynomial x power p minus 2, right? Since a to the power p minus 2 is equal to 0 and x power p minus 2 is irreducible, what will have minimal polynomial for a x power p minus 2 is minimal polynomial for a. If a satisfies any lower degree polynomial, no, because this is irreducible over Q. That is important. Okay, so if any lower degree polynomial which satisfies A will divide this, because this is minimal anyway. Mu x has to divide x power p minus 2, but x power p minus 2 is irreducible. That's why this should be minimal polynomial only. Okay, this is minimal polynomial for A. So what is degree of extension for this? This is of degree extension P, right? This extension is P degree extension. Now here this can also be thought of as Q A attached with theta P. Now if you see here, theta P satisfies x power p minus 1, which is polynomial in Q. Zeta p power p minus 1 is equal to 0. From here we will get this equation, zeta power p plus zeta power p minus 1, p minus 2, and so on, plus zeta plus 1. This also is equal to 0 because zeta p is not equal to 1, it is primitive root of 1. So this is irreducible, x power p minus 1 plus x power p minus 2 plus and so on, x plus 1. This polynomial is irreducible, and this Morey polynomial for zeta is minimal polynomial or zeta p over q. Okay, this is important. So there is a chance that okay, what is minimal polynomial over mu zeta over qa? What it is? Because zeta satisfies this polynomial, and this polynomial belongs to q as well as qa. So mu x qa, mu zeta qa, this divides uh, x power p minus 1 plus and so on, x plus 1. This implies that degree of mu zeta qa, this is less than or equal to p minus 1, because this degree is equal to degree of extension, okay, here in this case. So this is L over qa. So we got two equations. Okay, first one is that from here qa over q, this is exactly equal to p, and from here this is less than or equal to p minus 1. So it will be used in it after few minutes. So now what? This degree extension is less than p minus 1. Overall degree of extension L over q, this is equal to L over qa, qa over q, this is less than or equal to p into p minus 1. So and also if you had initially q zeta here, q zeta p here, then this was extension p minus 1 exactly. So p minus 1 using this extension, using L over q zeta p over q vc, and this extension and q zeta p over q, this is p minus 1 degree extension. This is Galois extension, we know, right? This is okay, nice. So this says that p minus 1 divides L over q. And from here also it is clear, L over q, and using this L to qa to q, this and qa over q, this degree is equal to p, implies p divides and this L over q. So what we get here, and p minus 1 are co-prime, p minus 1 are GCD is equal to 1, implies p into p minus 1. This number is same as L over Q. So this is one calculation. How it follows? These two will imply that it is less than, and next from star double star, or what, from this part. This is from star and double star implies this. Now let me call it capital star. Then from capital star, it follows that L over Q is same as P into P minus 1. Okay, so let's see what automorphism group of L is. Okay, aught L over Q. What is this? And we'll see the cardinality of this. Then we are, if they are equal, this will be Galois extension, and at that moment, the automorphism of L over Q will be the Galois group, and that is one part of the question. Describe the generators of Galois group. ठीक है, okay. Let's first calculate aught L over Q. So we have two generators of L. We have two generators of L. L over Q as field, as algebra, okay. They are A and zeta P. So any algebra homomorphism or field automorphism, field homomorphism, automorphism, whatever, if you define that where A is going, where zeta P is going, then any automorphism is well defined, right? For example, what elements of L look like? So you just have some idea of it. A belongs here implies A is equal to some Fi of A, some Fi is some polynomial, and Gi of Gp some polynomial I from 0 to some finite number where Fi and Gi, this belongs to Q X. Okay, so these are all elements. You are thinking about fractions, then you should you might be familiar with this because L is algebraic over Q. Since Q A and zeta, this algebra is same as taking fractions, right? Because A and zeta P both are algebraic, that's why we can write A like this. Oh no, we should take some element X here. X can be written in terms of polynomial of A and zeta P. Okay, so or this can be directly written as in two variable Fi of A comma zeta P, where Fi belongs to qxy to okay. So it is enough to define where a and zeta p are going. Then sigma belonging to odd LQ if and sigma of x is equal to f summation sigma of x is equal to I from 0 to n, because sigma is algebra over Q, algebra homomorphism over Q. So sigma will go inside everywhere. So because it is field automorphism, field homomorphism in fact, sigma. So it is also ring homomorphism. It will become Fi of sigma A or sigma zeta P. So better you just know about where A and sigma, sorry, where A and zeta P are going. So this was a little bit about why generators define. We need only to define on generators. Where A can go, where what choices for sigma of A. Sigma of A, if you remember, if mu is irreducible polynomial for x, minimal polynomial over x, then what all the conjugates of it, sigma can match to only conjugate. Means if a0 of f, okay, and sigma sends zeros of f to zeros of f. That's all. So let mu aq be minimal polynomial for a over q, then sigma a can go anywhere in v of mu, right? Zeros, zeros of mu. Zeros of this polynomial. See. Okay. So how many, because cardinality of this is what? Sigma of A has how many choices to go? Cardinality of VC A Q, that is equal to mu VC of x for P minus 2. This is our irreducible polynomial for a choices equal to P choices to go. What are these choices? Explicitly, a sigma of sigma A belongs to a zeta p, a zeta p square, and so on, a zeta p power p minus 1. Okay, so it has p choices. Now choices for where we can send zeta p. Choices for sigma of zeta p. Where it can go, mu zeta p of q be minimal polynomial over Q, then uh, sigma A belongs to V of C mu zeta P Q. So sigma of zeta P has this much only, VC mu zeta Q choices, which is same as VC of x power P minus 1 plus x power P minus 2 and so on, x power x plus 1. Okay, so this has exactly P minus 1 roots, so P minus 1 choices. What are these choices? Sigma of zeta P should belong in this zeta P square and so on, zeta P for P minus. Okay, so these are exactly the choices where zeta P can go through an automorphism of L. So there are there are at least this much P into P minus 1. Any automorphism is defined by where A and zeta P are going. So this many choices we have, P into P minus 1. There are P into P minus 1 distinct automorphisms. These are all distinct automorphism, at least P automorphism of L over Q. But if you see aught L over Q, this group, which is, we don't know if it is Galois or not, cardinality of this set is less than or equal to degree of extension L over Q by Dedi-Kind-Arting. But this is exactly P into P minus 1. We have calculated it. So, and we have at least into P minus 1 automorphism of L over Q. What we get? This implies automorphism of L over Q. This is of the cardinality P minus 1, and hence L over Q is Galois extension. Is there anything left that we had to prove? This is Galois extension. We have shown this. Describe the generators of Galois group with their action on A and zeta P. We have defined only our Galois group, just like on generating set what they are giving. Okay. So second part is done. We have to show what are the generators of automorphism group. So we have our group. So what is this group? So first let's see what is this group. We have denoted by G uh, and Galois group of L over K. We are denoting everything. And okay, order of P is P into P minus 1. So because P is a prime, by Silo theorem, Silo first theorem, there exists some P order subgroup of L by Silo. There exists P order sub, say H, because H is uh, prime power order, sorry, prime order. So H is like cyclic. Okay. Uh, okay, so H is cyclic. Is this normal inside G? And also that G is abelian or not, we have to check that also. How to see that? Here we have. So first of all, let me focus and see what we want to prove. Okay. Describe the generators of Galois group. So first of all, we have described what are all the elements of. Okay. So this will do later. Let me denote G with sigma ij. Okay. And I will show sigma ij, which are from L to L morphism, such that sigma ij of A is equal to A into zeta p power I, and sigma ij of zeta p, I'm just describing where generators of L is going, zeta p power j, okay, where I is equal to 0 to p minus 1, right? And j is equal to 1 to p minus 1. So this is our D. I have explicitly defined uh, what are our automorphism. Sigma is the automorphism of L over Q. And this is our G. And we want to find what are generators of G. So there exists A into zeta P is of order P. So G can be written as the cyclic group generated by A into zeta P cross product with zeta P. Is this correct or not? So let me first ask if C is abelian or not, because writing product of cyclic group, it will become, is Z abelian? Let's see. Take two elements, for example, sigma 1 2 and sigma 2 1. Okay, sigma 2 1, and let evaluate on A, and we should have question mark here. Sigma 2 1 first, written, and sigma 1 2. Okay, if this is violating the rules, then G is not abelian, of course. So let's see where this will map. A to A into zeta P to the power 2, right? Here we have 2. Now we will just apply here 1 2, and this is equal to sigma 1 2 of A and sigma 1 2 of zeta P square. But because this is ring homomorphism, this becomes whole square here, goes outside. So but sigma 1 2 of A is just A into zeta P into what sigma 1 2 of zeta P is zeta P square. Outside we have a square, so this becomes A into zeta P power 5. And this side what we have, sigma 1 2 means applying on A, this becomes sigma 2 1 of A into zeta P. 1 is here, so zeta power 1 here. Now sigma 1 2, sorry, sigma 2 1 of A into sigma 2 1 of zeta P, right? And this is equal to sigma, sorry, here we have 2, so zeta P power 2 into, this goes to zeta P only, right? Because here we have 1. So what is this? Is these are not equal. So this is not equal. Okay. This answer is no. But we have this that there exists p order element. There exists p minus 1 order element. Oh, sorry. Is there p minus 1 order element? Okay. First of all, these are not elements of G, so we cannot write that. G is not abelian. So what it can be? What kind of G is? G is of, there exists, but all we can say, there exists p order, there exists a p order subgroup, because p divides G. Let me this is silo p. So is this unique? That is the question. Silo p, n p is congruent to 1 mod P and NP divides P minus 1. So NP is congruent to 1 mod P implies NP is equal to 1 plus pk of this type. Okay. And not here. 1 plus pk divides P minus 1. This implies k should be 0, and because this will be bigger than P minus 1, so NP is equal to exactly 1. So there exists unique CLO P subgroup of C. So let's say H is subgroup of G, order of H is equal to P, and this is unique, so it is normal. This is CLO 2, okay? CLO 2. Unique subgroups, unique CLO P subgroup is normal. Order of H is equal to P. Now what? We have actually we have described what our G is exactly here, and how is sigma Ij they are acting on A and zeta P. Uh, this is completed. This is part B is completed. Is this part B? Yeah. So I'm not going to write explicitly generators of G because we don't know G is non-abelian. And yeah, so we are not sure what will be that. Used to establish, I'm looking at part C, establish the canonical isomorphism of C onto of affine group A1FP maps, linear maps F from FP to FP, where U belongs to FP star, V belongs to FP. So yeah, let's see. We have already seen description of C, right? What kind of C looks like. I'm just looking for C. Define G2, let me call it phi, A1 FP, this morphism send phi of sigma Ij to map F from FP to FP. This is not set. I'm sending sigma Ij to a map where F of X is going to, sorry, I plus Jx, or let me write like that, Jx plus I. Note that J is running from, this belongs to set 1 to P minus 1. and this belongs to 0 to p minus. So this is actually map in this is element in A1FP. Okay, so how was sigma j defined? Let me recall for you. This was A into zeta p power I sigma ij or sigma of ij of zeta p. This was defined as zeta p power j. And note that this was the case that j belongs here and I belongs here. We are sending this sigma ij to this map j x plus I, or this is our fx. This is how our f is defined, image. Okay, so from here, is this size 1 onto its isomorphism? That is what we want to see, right? Apply isomorphism of the is this isomorphism for any this kind of map where j belongs to fp star and I belongs to fp. So this, from now on, this is my notation for A1FP. Okay. So I will just write element wise description of fx. I will just write fx. That is this. This describes what is f. Okay, so we know our phi. We'll see what is this homomorphism or onto 1 all this. Phi is 1 How? This is clear, right? If j prime x plus I prime is equal to j x plus I prime in this FP ring, this will imply not I prime here. Polynomial description, how we compare the polynomial. From there, we get j is equal to j prime and I is equal to I prime. This implies sigma ij is same as sigma j, I prime, j prime. So this is 1 size also onto for any jx plus I, we have sigma ij in G, such that phi of sigma ij is equal to jx plus I. So this is 1, 1 and 2. We have to check it is homomorphism. Phi is homomorphism. For that, we have to see phi of sigma ij composite, let's say Rs, is this equal to phi of sigma ij composite phi of sigma Rs. Okay, so let's see from which side we should start. Uh, we'll start both sides. Okay, phi of um, okay, so when these two maths are equal, these two maths are where these two are elements from A1FP. This side, what is this side? First of all, let me write this. This is Jx. Okay. Apply to some element of, it should apply to some element of A1F, some element of FP, that is X. Evaluate at X, both sides. If they're equal at every point X, then we are, so we'll first apply this and then we apply this. What we'll get here, this side is Sx plus R. This is element in FP again, and we are applying sigma, this math, phi of sigma ij, applying on this. But next step, it will become j into Sx plus R plus I, and this is equal to j s x plus rj plus I. This side we are getting this, so we should get the same thing this side also. Okay. Okay, so here first we'll calculate what is inside. So this is a little bit tricky, but not where A is going will decide. Sigma ij composite sigma Rf applied on A. This implies that sigma ij is as it is applied, it will become A zeta P power R, right? And once more, if you see sigma ij here into A sigma ij here, zeta P power R, this becomes A into zeta P power I into, this becomes zeta P power Rj. So this is A into zeta P power Rj plus I. Okay. Now coming to where zeta P is going, sigma ij sigma Rf theta P applied on zeta P, this becomes I'm not calculating left hand side right now. I'm just calculating what is inside. Okay, this part. So this will become sigma ij of zeta P power S. Now in the next step, it is nothing but zeta P power Sj or Js. So this calculation implies that sigma ij composite with sigma rs is same as sigma of, first we write where a is going, this sigma of rj plus I comma. I'm not writing anywhere comma here sigma ij, but because this is complicated, so we don't mix up the things. For that, I can write in bracket also this number sj, this number, two numbers. But when we apply, so psi of sigma ij, sigma sigma rs, this equal to psi of sigma rj plus I sj. This is nothing but sj. If you now evaluate at x, sjx plus rj plus I, which is same as this, right? So hence we have found that phi is homomorphism. So phi is homomorphism 1, 1 and 2. So this is group isomorphism. Okay. G is isomorphic to A1 FP. Okay, so after solving this, we'll see D part. Draw the diagram of lattice of intermediate fields L over Q. Set is of subgroup G, indicating the various containment which intermediate fields of L over Q are Galois over Q. Okay, so this is long question. Part D. G is isomorphic to A1 FP, right? Which is the collection of this kind of. I'm just writing UX plus V, where U. Okay, this is okay. U belongs to FP star and V belongs to FP. Note that after multiplying those, this is also an element of A1 FP, because S is non-zero, J is non-zero, that is belonging to FP star. So the product is also belonging to FP star. So this is that is also, you have to note it. So after this, calculate all the subgroups. This sub calculation of this subgroup is easy. We can calculate all the subgroups, and then because L over Q is Galois, we can use Galois correspondence using Galois correspondence. we can calculate this corresponding. We can calculate. But for one, because there exists unique silo P subgroup, which is H, which is normal inside V. We have we get an intermediary field and intermediary intermediate field water intermediary field like this. Here we have L, which is Q A theta P. Here we have LH, which is also sometimes noted as L fix inside L by H. And here we have this identity group. Here we have H. Here we have G. This kind of order reversing Galois correspondence. Here we have Q. So H is of order P, order of H is equal to P. I'm writing all again and again. So please. So this is our P degree extension. Here we have H, that is L over LH. This extension is equal to H with trivial subgroup. This quotient. This is equal to P. This extension is prime extension. So no intermediary fields in between can exist. And what is this? You can explicitly calculate it, right? What this would be? Q of zeta P. This extension is P minus 1 and this extension is P, right? So LS should be explicitly, LS is nothing but Q of zeta P, and since L over LH is prime, that there is no intermediary field between them. There is no intermediate field between them. What left is that what are intermediate fields? The left part is the left part is what are intermediate field. With this section Q theta P over P. Proof will be given in next. Okay. For now, it is an I'm leaving it as an exercise. I hope there is similar question below. We'll solve that. So we'll see what are intermediate field between them. Okay. So let's see next part. So we have f, a polynomial like this. Fx is equal to x power 4 minus 14 x square plus 9 uh, 3 by Sridharacharya formula, we can factor it, right? X square. Uh, what are roots of it? First of all, let me calculate roots first. Lambda is equal to minus 14 minus 14 plus minus under root b square minus 4ac, that is 14 square minus 4 into 9 divided by 2a, that is just 2. So you take uh, under root 4 common outside, so what left is that 14 plus minus, it becomes 2, and here just 7 square, which is 49. Here 9 and 2, it's just 9, right? Because 4 is taken outside as common. And what is this? It just becomes 7 plus minus 2, cancel with 2. It is 49 minus 9 is just 40. And this can be written as 7 plus minus 2 root 10. Okay, so it is just 2 root 10. So we have calculated 2 roots of this. So what we can write here, this is x square plus 7 minus root 7 minus 2 root 10 and x square minus 7 plus 2 root 10. Okay, so what more can be done here? From here, we just continue with our calculation. 7 can be written 5 plus 2 plus minus 2 root 10, and 5 can be written under root 5 whole square plus under root 2 whole square plus minus 2, and this can be written as under root 2 and then under root 5. So after all, this becomes root 5 plus minus root 2 whole square. So you can just put it like that. So this is x square plus root 5 plus 2 root 5 plus root 2 whole square. This is 1. Another box is x square minus root 5 plus minus, is just plus minus. Okay, sorry. In 1 it should be plus because we are getting 2 roots. So lambda 1 should be root 5 plus root 2. Lambda 2 should be in minus. So 1 is in plus and 1 is in minus. Okay, these are roots. So this in fact this would be minus. When you are getting roots and you are x minus a should be the factor. So here it is minus. So one root is this box, another is this where it is square. Now what happens is you can just factorize x plus root 5 plus root 2 x minus root 5 minus root 2. This is first factor. In the second you have x plus root 5 minus 2. In the second you have x plus x minus root 5 plus 2. So you are getting 4 roots. So F has got all four distinct roots root 5 plus minus root 2. So if you attach splitting field of F, u root 5 root 2. If you just attach root 2 and root 5 over Q, then F has all its root inside this. Okay. And one more thing, uh, it is just equal to Q root 2 plus root 5, right? So just attaching one root of F. You are just attaching one root of F and you are getting all the roots here because all the four roots are here. So this is Galois extension of extension 4. We have seen this. Why I am directly writing this? This is discussed in previous section, previous slide section, discussed previous live. So this extension is simple and just given by one of the roots. So what is Galois group of? Let me denote it as L. Q root 2 root 5, or you can just write plus here over Q is of degree 4 extension, Galois extension. Okay, so I don't think we should discuss more about this because this is already been done. Determine the Galois group. Use the rational root test. F has no rational zero. Actually, we have calculated all the zeros. We are not rational. So F is 0 to square and of 4 degree over Q. Okay, so part B is draw the diagram of lattice of intermediate field Paris containment, which intermediate field are Galois or Q. This is also discussed in the last part, but part B, I can just draw the diagram. Galois, part B, Galois of L over Q. This is equal to Z2 cross Z2 or isomorphic to. This is given by sigma 1, which is the identity of L, sigma 2, which is defined as I'm just defining one root where this primitive root is going. Root 2 goes to minus root 2. Sigma 2 of root 5 goes to root 5. Sigma 3 of root 2 goes to root 2. Sigma 3 of uh, root 5 goes to minus root 5. How sigma 4 I'm defining? Sigma 4 of root 2 is just minus root 2. Sigma 4 of root 5 is minus root 5. These are four elements. Then for subgroup, we have this lattice. Here trivial. Here we have trivial with sigma 1. Then identity with sigma 2. This is also subgroup. This is identity with sigma 3. You just check it out. They are subgroups. Okay. For corresponding diagram for lattice, or fields is for identity, we have identity fixes all of the elements of L, where sigma 1 fixes identity fixes anyway, all of them. Sigma 1 fixes, oh, sorry, this is sigma 2, this is sigma 3, this is sigma 4, because identity is sigma 1. Okay, so what sigma 2 fixes? Root 5. So this is just q root 5. Here we have everything is fixed by in q. So what sigma 3 fixes? Sigma 3 fixes root 2. So this is q root. What sigma 4 fixes? Q root 10. So this is done. This is also discussed in the same way, where we had random p and q prime co-prime with each other, distinct prime, and we had found that q is, this is simple, q root p plus root q. This is done there also. Anyway, so let's come to next question. So we have still 15-16 minutes, I think. Eight 8.5. L over K is the Galois extension of number fields. Number field is finite extensions of Q. K is subset of real number. So that either L is also real field or L contains a subfield of real number, such that degree of extension L over E is 2. L over E over K. K is contained in any way R. So question is of existence. There exists such E or not. For that, we will use just hint, okay, and we'll take automorphism of L over Q. We'll take conjugation action of L, conjugation action of C, identity of C, and complex conjugation. This is subgroup of G, which is odd. We'll just read the hint and no need to solve it. If L is not real, then we have to show there exists 2-degree extension, sub extension of degree 2, L over E. Okay. Yeah, not substation, I would say, but intermediate field of this basically. Then a complex conjugation L to L, which is restriction map of C. Okay, because L is subset of C anyway. Z goes to Z bar. Is non-trivial K automorphism because K is contained in R, and R K element. All the elements of R are fixed. So in particular, elements of K are also fixed. So we can say they are K automorphism. So Z going to Z bar is an automorphism because elements of K are fixed. It is K automorphism. So its order is 2 because once you take z goes to z bar and z bar goes to z bar to the whole bar, and it becomes z. So it is of order 2. Since every z inside L, we have z bar is also contained inside L, because the same minimal polynomial gives that z and z bar both are roots of them. Okay. Here is a polynomial description which belongs to kx. Why kx? Because this is also fixed and this is also fixed by sigma, which is complex conjugation. So this would belongs to ground field with constant fields. Okay. Okay. So what else? Therefore, Galois correspondence for this H, which is subgroup of order 2, will get this LH, or fixed field of L by H, is real. It is real means why? Why it is? Because complex conjugation fixes only real numbers inside complex numbers. So better E should be subset of real number. So it is real number, and as usual, by Galois correspondence, degree of extension is equal to order of H, which is equal to 2. Okay, so I hope you understood this. If you have doubt, you can type into comment box. I will try to reply when I will get time. So, yeah. Now next question. Eta B eta B some element inside QZN, where QZN is sorry QGN, QGTN, where QGTN is NS cyclotomic field. Yeah. We are attaching nth roots of unity, primitive nth root of unity to Q, such that Q eta is maximal subfield of Q theta n, and so that degree of extension is 2. So again, we'll follow the hint, and I'm not going to solve it because it is already solution, right? Sigma belonging to Galois group of this extension the complex conjugation, and we know its order is 2. So we'll get cyclic subunit by sigma of order 2, which is subgroup of Galois group, has order 2. Now we'll calculate fixed field of H, and we'll get that because this is our H of order 2. Okay, we'll get 2 degree extension, and any middle part, any k which lies in the middle, will be either this will be equal, so not either in this case, either k is equal to E or k is equal to L, right? Because degree of extension is 2, simply. And why E should be simple, means generated by single element, that is described here. This is our LH. For E, we are denoting here. Part B, let's say here we have L, here we have LH, which is Q, zeta N. Okay, so why this is Q of eta? Question mark. This is main part. Let eta be this. Then eta is fixed. This implies eta is belonging to LH because its conjugate, eta conjugate is eta only. So it is a subset of LH, and particularly Q eta, it becomes subset of fixed field, and fixed field is anyway subset of bigger field. Moreover, this fixed field is explicitly equal to Q eta. Why? Because this degree of extension is here we are taking Q eta inside fixed field. So this degree of extension is 2, and this degree of extension is less than or equal to 2. So in particular, all the equalities are equal here. This is equal. Okay, because zeta satisfies this polynomial over Q eta. Okay, so that's all. This implies Q eta is equal to LH. So this is what we wanted to show. That there exists sub extension of extension degree 2, and which is simple. So Q eta simple. So let's see if there is more questions. We have 10 more minutes left. So that for each divisor D of P minus 1, there is this unique intermediary field E of field extension QP over Q. So we know that Galois group of QP over Q, this is isomorphic to ZP star, right? And ZP star is cyclic. Why? Because it is finite group, finite subgroup of multiplicative group of a field, multiplicative group of a field, that is FP star. In particular, it is nothing but FP star. So, okay, ZP star is cyclic. So, corresponding to any what is its order? Okay, that is also required. Order of ZP star is equal to P minus 1. So, corresponding to any divisor D of p minus 1, there exists unique subgroup because it is cyclic. So it is for any divisor D of p minus 1, we'll get unique subgroup of that p star of order D. So unique subgroup means we'll get corresponding, for example, E here, H1, H2, and so on. Here we have that P star. Then here, this side we will have uh, QP containing QPH and so on. Here we will have Q. Okay, such kind of because corresponding to any divisor D, we'll have a unique subgroup. So corresponding we'll have unique subfield also. So result follows from Galois corresponding. Okay, so let's see if there is anything left. Uh, yeah, so follow the hints. Almost all of them are given in the solution. We have next question here. Here also we are getting hints, so I'm not going to solve it. We are almost out of the time, but uh, I can discuss what it is saying so that q cos 2 pi k by n is same as qn cosented with, sorry, intersected with r. This is fine. What is nth root of unity? Part A. Q is anyway subset of R, right? Uh, what else? Cos 2 pi n by k by n. This is also belonging to R. Now Q is subset of Q also. That is Qn. I sorry. Is this cos 2 pi n 2 pi k by n? Question is here. Is this belonging to R? If it belongs to R, I will just write what is happening. So this will imply that Q n intersection with R. This is just attaching cos 2 pi k by n. It's contained here. I will just say like, okay. Is this is equal or not? That will be done later, right? But in Qn, what is primitive nth root of unity? E power 2 pi ki by n. This is our primitive nth root of unity. Okay, so this is nothing but cos 2 pi k by n plus I sin 2k pi by n. Okay. So once this belongs to this is primitive root, so its conjugate is also e power minus 2 pi I k by n. This also belongs to Qn. In particular, this is same as cos 2 pi k by n minus I sin 2 k pi by n, right? Now add them. If you add them, you'll just get that cos 2 pi k by n is equal to e power 2 pi I k by n minus plus cos 2 pi I, sorry, e power 2 pi I k by n. This is in minus divided by 2. And this belongs to, and this is also equal to, yeah, if you write, in particular, this belongs to, this is real, that is clear. Sorry, this was not the real question I was asking. This belongs to R. So cos 2 pi k by n. Is this belonging to Qn? Yeah, this was question. So this is already written somewhere previously here. Okay, here. Q is subset of R. This is also subset of R. So this is subset of R is clear, but Q is subset of Q1 is clear. Question is here. So, and this belongs to Qn because this is a primitive nth root of entity. This is primitive nth root of entity. So this is clear. Once it is like that, so we got this. Other side, what should we do? How to show the other side of it, the other inclusion. Let x belongs to Qn intersected with R. Then what is happening here? Conjugation action x bar is equal to x. This implies what? So first of all, I just proved either Qn is already inside R or there exists real subfield E of R which contained in R, which is contained in Qn also, such that Qn over E, this degree of extension is 2. That is elements which are fixed by complex conjugation. So this is the collection. This is subfield that we are talking about. The elements which are fixed by complex conjugation. So how should we do this? We have an one idea is that x belonging to here, which is given and which is in here. So x can be written as some polynomial of e power I 2 pi a by n. Okay, some polynomial or some belonging to q. Then to become when it becomes real, when x is real or x belongs to R. That is the coefficients of I, they vanish. Yeah, they vanish or their square becomes -1, something like that. Or 4 become +1, or multiple of I become 0. That's all. This implies this x can be written as f of cos t plus I sin t. Okay, sin t for finding the t is 2k phi. But if whenever find whenever coefficient or multiple of the will vanish on if I square becomes -1 or some it is 0. Disappears. When vanish means disappear. Vanish. Coefficient vanishes. So x can be written as some polynomial g or depending on cos t and the sine squared. Okay. Now sine squared t can be also I'm just writing sine square. Why? Because I square when I square becomes -1, sine is multiple of I, so sine it becomes sine square. So this is this sine square. Yeah? So g of cos t, but sine square t is 1 minus cos square t. Everything is reduced in a polynomial where only cos t appears. So this belongs to q cos 2 pi j y. Okay, this is how we do this. This is also, I think, discussed in a previous live session. You can check it out. Okay. Okay. So We are almost done. Let me stop recording.